And hello, excited chemistry students. You are so enthusiastic to watch all my videos. There's a short little video on how bond energies can be used to estimate the energy given off or taken in during a chemical reaction, called the enthalpy of the reaction. So yeah, a table. And they're common in every textbook, and Google it. You'll find dozens of different versions of it. But in these tables we have the bonds listed that might occur between mostly nonmetals. In those bonds between nonmetals, forming covalent bonds, can be used to say, well, if a chemical reaction happens, we could think about it as maybe breaking some bonds and forming new bonds. So if I were to do a chemical reaction where I break some carbon-hydrogen bonds, 1 mole of carbon-hydrogen bond would require, 6.02 times 10 to the 23rd carbon-hydrogen bonds would require an energy input of 414 kilojoules. Similarly, for a hydrogen-hydrogen bond, and the double bonds are also listed, so a carbon-carbon single bond is easier to break than a carbon-carbon double bond. I'd have to put in 611 kilojoules to a mole of carbon-carbon double bonds to break those. And the list goes on and on. And this gets even more extensive if you like. Here's an important exception. Carbon double bond O is 636 kilojoules. But in carbon dioxide, it's actually even a little bit more stable than that. So it would require adding 799 kilojoules to break up 1 mole of carbon-oxygen double bonds. But each carbon dioxide molecule has 2 of those carbon-oxygen double bonds. So if I was going to break up carbon dioxide totally, that would be 2 times that 799 number, and that's a whole lot of energy. Just illustrating that carbon dioxide is a very stable molecule. Here's the general rule we follow, the general pattern we always follow. There's a simple way to remember it. I just think about bonds broken minus bonds formed. The H numbers, excuse me, I have a frog in my throat, so to speak. Yeah, I don't eat frogs. The H numbers are called enthalpy numbers. I commonly think about them as heat numbers. H stands for heat, although it's not technically heat, and there's a small difference. We'll get into that in a later chapter. But think about it as heat if you like, heat energy. Or sometimes it's labeled in our textbook actually a delta E, the change in energy. And the D is the dissociation energy needed to break the bonds. And D is the dissociation energy needed to break these bonds. But I think about the bonds being broken minus the bonds being formed, looking at the difference or the comparison between the two. Some books use little coefficients representing the stoichiometric number of bonds being broken in a particular molecule, or also important is the number of molecules that you have. Let's just use this a couple times and get some good examples going. In one approach, we can think of breaking all these bonds in the reactants and forming all these bonds in the products. If you've practiced this a couple times or think about it, there's a simpler, faster way to do it if you're careful about your observations. But I could write, let's see, I'm breaking 1, 2, 3, 4. So let me imagine breaking all those 4 bonds. I listed it right here. 4 enthalpies of the carbon-hydrogen bond and 1 enthalpy of the chlorine-chlorine single bond right there. So those are the bonds broken minus the bonds formed. And the bonds formed are, I'm forming 3 carbon-hydrogen bonds here. I'm forming 1 carbon-chlorine bond here, and I'm forming 1 hydrogen-chlorine bond here. So I listed those all out right here. Again, that's bonds broken minus bonds formed. I look up all the numbers on the table above, carbon-hydrogen, chlorine-chlorine, unless I made a mistake, which I often do, so feel free to just give a shout out if I screwed something up. You know I always do that, just to keep you on your toes. 3 of those bonds, 1 carbon-chlorine bond, 1 hydrogen-chlorine bond, and it comes out to negative 113. When a delta H or a delta E is negative, that implies it's exothermic, and that means it gets hotter, gets warmer, gives off heat to the environment. Alright, let's try another one. Oh, no, wait. There's another approach. Instead of imagining, this is the same reaction I had above, instead of imagining breaking all the bonds over here and forming all the bonds over here, I might more carefully observe that really only this bond is broken, or I could consider this bond only to be broken. I'm not quite sure the mechanism involved in this reaction, but I would imagine I'm not really breaking these bonds. I'm just going to break this bond, and I'm going to form a bond with one of these chlorines, but I'm going to break this bond as well. So I break this bond, and I form this bond, and I form this bond. In a way, that's a lot simpler. Fewer numbers to worry about. So I'm going to break one carbon-hydrogen bond. I'm going to break one chlorine-chlorine bond. I'm going to form one carbon-chlorine bond, and I'm going to form one hydrogen-chlorine bond. And that comes down to this, same number. Not surprised. Should be the same number. Or you can also say, take that original full measure of breaking all the bonds. So if I imagine breaking all the bonds here and forming all the bonds over here, I had written this. But if I look at this carefully, don't you see something cancels? Yeah, I'll show you. Let's see, where is it? Yeah, there we go. So I said this could also be thought of as saying, well, if I have 4 of these 414s on the left and I'm subtracting 3 414s over here, those 3 go away, or in other words, 4 minus 3 is 1, 414. In other words, I get the same answer. So bond broken, bond formed, voila. It's always good to get a mental picture in your mind of what's happening. Here's the combustion of methane. Let's try another example. Combustion. In the combustion, I'm combining with oxygen quickly, and I almost always get carbon dioxide and water when I'm dealing with just a simple hydrocarbon. And the smaller the hydrocarbon, the cleaner it burns, which is nice. But I still get carbon dioxide, a greenhouse gas. Shoot. Anyways, so I'm going to imagine breaking all these bonds, because over here I don't have any carbon-hydrogen bonds at all. And I'm going to imagine breaking this bond as well, because over here I have no oxygen double bond in the form of an O2 molecule. So again, I wrote just simply bonds broken minus bonds formed. What am I breaking? I'm breaking 4 of these carbon-hydrogen bonds. I'm breaking 1 here and 1 here. That's 2 oxygen double bonds. I'm forming 1 molecule of CO2, which has 1 carbon-oxygen double bond here and 1 carbon-oxygen double bond here. Maybe I should have written that, but soon you should know that carbon dioxide is carbon double bond O for both of them. And I'm forming the oxygen-hydrogen bond here, 1, 2, and 3, and 4. So that'll be a total of 4 oxygen-hydrogen bonds considered. Oh yeah, in that table above, do you remember I was pointing out the difference between a carbon-oxygen double bond and a carbon-oxygen double bond in the carbon dioxide molecule? So I just made a quick note here that I'm dealing with the carbon dioxide instead of just a simple carbon-oxygen double bond. So from above, that picture above, I said I was breaking 4 carbon-hydrogen bonds, breaking 2 oxygen double bonds, dissociating. I think our book does use the D for dissociation. And I'm forming 2 carbon-oxygen double bonds in the carbon dioxide molecule. There's 1 molecule, but there's 2 of those in every molecule, and forming 2 molecules of water, but each water molecule has 2 of those OH bonds, so there's a total of 4 OH bonds considered there. And again, an exothermic, negative 802. Of course, when you burn something, it's going to give off heat, exothermic. Again, that means if I had 1 mole of methane and 2 moles of oxygen to give 1 mole of carbon dioxide and 2 moles of water vapor, that quantity of combustion for the methane would release 402 kilojoules. If I divided everything in half, that number would also divide in half to 401 kilojoules. So if I had a half a mole of methane and 1 mole of oxygen to give a half mole of carbon dioxide and 1 mole of water, then that would be, half that number, 401, negative 401. Another cute example. Here's nitrogen and hydrogen reacting to give ammonia. Nitrogen is an N triple bond. Hydrogen is a single bond. Write it like this, think about it like this. But I had to balance the equation. I stuck a 3 here to get 6 hydrogens here and 6 hydrogens here and 2 nitrogens and 2 nitrogens. So really I have 2 of those. So I might imagine breaking 1 of these bonds, or a mole of those, breaking 3 moles of these bonds, hydrogens, and forming 2 moles of these molecules, which involves 1, 2, 3 nitrogen-hydrogen bonds apiece. So that's really going to be 6 nitrogen-hydrogen bonds forming. And I'll think about subtracting that out. Yeah, so if you follow this convention, bonds broken minus bonds formed for the bond energies, and think about the minus, it will always give you the appropriate sign on the delta H. This one comes out to negative 80. So I look that up in the table, take it times 3, look this up in the table, take it times 6. I think I have one more example, just for entertainment purposes, because I know you're not entertained enough yet, right? So here's my next reaction. Ethene with a double bond reacts with hydrogen gas, both pretty reactive, so it'll go, no problem. But I might think about breaking this bond totally. I might think about breaking that bond totally. And when I do so, I'm going to imagine forming a new bond, a new single bond between the carbons. And one new bond between this carbon and the hydrogen. So one of those hydrogens goes on to this carbon, and the other hydrogen goes on to this carbon. Think of it that way anyway, and that's likely most of the time the way it might happen. Or if this one doesn't, if this one goes to this one, this particular atom might not go to that one, but it probably would. Long story. Anyways, and so I'm not going to break all the bonds. I'm just going to break that one, and I'm going to form this one, and this one, and this one. And I wrote that out like this. And I think, yes, that looks good. Trying to see if I made a mistake. You never know. So I'm breaking one carbon-carbon bond, double bond, breaking one hydrogen-hydrogen bond, yes. And that's the reactants, bonds broken, minus the bonds formed, the products, carbon-carbon single bond, and carbon-hydrogen single bond, 2 of those. You might say, is there a comparison between this and this that would allow me a simplification, this and this? I wouldn't do it that way. I would just say, imagine breaking that one totally, forming that one totally, breaking that one totally, forming those totally, and yeah, exothermic again. So if I had 1 mole of these and 1 mole of these to form 1 mole of these, I would release 128 kilojoules of heat. Hey, thanks guys. See you in class soon. Thanks for your hard work. Seriously.